The solutions are just secondary, second order differential linear equation.
Yeah, it's a second order linear differential equation, and those are the solutions. And so the solutions to the wave equation are plane traveling waves. All right, another complication is, so traveling waves, okay. This is the aspect that says it's a traveling wave. What does plane traveling wave mean? Okay, and here's where it gets funky. All right, so say I'm the electric field right here. I'm at this point Z, and the value, the magnitude of the electric field equals 4. Right? So most definitely the value of the electric field at Z equals, Z0. At Z equals Z0, the value of the electric field is 4. All right? And there's a value of the magnetic field. Right? The magnetic field is going to have some value right there at Z equals 4. All right? What is the value of the electric field? Where is it for? Okay? So where is the electric field for? The electric field is for at Z equals Z0, right?
Oh, is that when the peak is on the wave?
Yeah, but it could have been anywhere. But say that number is 4. Okay, so say this is the Z direction this way. All right? The Z direction is this way. All right? So I'm at Z0, and the value of the electric field is 4. Right? But what is this whole plane that I'm living in right here? So Z is this way, but what is this plane like this?
Why?
Look on camera.
That's
Okay.
it's all 4.
It's the XY plane, right? Okay, so this is the XY plane. I'm at Z0. The value of the electric field is 4, and it's 4 at Z0. But where is it 4 in the XY plane?
Everywhere.
Okay, and the answer is everywhere. So everywhere in the infinite XY plane, the value of the electric field is 4. What's that? The plane sits at Z0, and in that plane, there's an electric field of magnitude 4 everywhere.
Even if you go to infinity.
Even infinity. And that's what a plane wave is. So that's a plane wave. So I'm a plane wave at 4, and I'm traveling this way. Because like say I'm 4 now, right? Let some time go by, that peak is now shifted over here. And now that plane is shifted here. So that plane wave
It's only 4 a period later.
right.
Because it would change.
No, so what you're saying now is if I'm 4 here, so say I stay at Z0, what happens to my value? I go down to 0, and then I come back to 4.
Right, but when you come back to 4 over
You can
one
look at it
period
two
later,
ways.
The
You can look at it 2 different ways. Yeah. Okay. Again, this is way off base, so I don't want to go too deep into here yet. Okay, let me keep going. So these are plane traveling waves. All right, and that's what we really need to solve this problem back over here. After all that whole discussion, what I find out is the solution to Maxwell's equation for the electromagnetic field are plane traveling waves. All right? So what I'm going to do here is I'm going to get rid of Maxwell's equations and just write plane traveling waves. So here are plane traveling waves. There's a big plane traveling wave coming, big plane traveling wave coming, big traveling wave coming, big traveling wave coming. All right, and Aldemar, you're concerned with plus or minus infinity. Here's the way out of it. The plane traveling waves themselves might not be physical. All right, but the plane traveling waves form a basis set, a complete basis set from which physical answers can be built from. All right? All right, so these plane traveling waves now hit these slits, right? Over here, you have, and then what you do is each plane traveling wave by this thing called Huygens principle. And what Huygens principle says is that the plane traveling wave can be built up in an infinite number of point sources. So here's an infinite point source, here's an infinite point source, here's an infinite point source for electric fields. And what you eventually see is that all the parallel components cancel when you add up all these point sources. And then what you're left with is just, the sum of this is just a value for E, value for E, value for E. So that all the sideways components cancel, and it just comes out to equal like an electric field this big of that value. Okay? But these point sources now, the point sources for of these plane waves equal e to the I k dot r minus omega t. So it's the same thing as kx, it's just the dot product. But what it means is that these are radial, equal radial or spherical waves. So what happens is when the plane wave hits this point source, and hits the two slits, it essentially picks out one of these points in the plane wave, and those points act like a spherical source. So there's, E1 equals e to the I k r1 minus omega t. And then here's another point source over here. And then this is like E2, which equals e to the I k r2 minus omega t. All right, so here's the big scoop, is that you started off with light. Light can be expanding in terms of these infinite plane waves. When those infinite plane waves hit the two slits, it looks like 2 point sources of waves that come out spherically. If I can now have 2 point sources for waves that come out spherically, can those waves interfere constructively and destructively?
Yeah.
And the answer is yes. All right? And when they interfere constructively and destructively, when you have constructive and destructive wave interference, you get an interference pattern. Right? And when, for example, if you wanted to find the intensity, say you wanted to find the intensity right here, the intensity at x. All right? Intensity is equal to the energy over the area times the time. All right? Energy, so now it's proportional. Energy is proportional to the total electric field.
Are you talking about the magnitude of the interference?
Yep.
The intensity?
Yep. So the intensity is essentially a number. How intense is the energy here? So what the detector measures is intensity. So when it's bright, it had a lot of intensity, and when it's dim, it had very little intensity. Okay, intensity is proportional to the energy. That's E for energy, not the electric field. Right? And the energy of an electric field is proportional to the magnitude of the electric field squared. Yep.
Is there a reason why the E, A, and T are in brackets, or is it
It's
just?
because I'm doing dimensions again. So whenever I put things when I talk about dimensions, I put them in brackets. So this is an energy bracket, that's an area bracket, and that's a time.
So, just
Okay.
like differentiating.
Right, yeah. And look, all the letters are recycled and reused. So what it's up for you guys is to have a level of understanding. And so what I always say is go home in your notes and put in, right energy, right area, right time, so you don't mess that up. right? And if you do that, then you're understanding. If you're not doing that to your notes, you'll have no idea what they are later. Right? So you've got to go through all that effort. Okay, so the intensity is proportional to the total electric field squared. All right? Now, the electric field at this point x is equal to this one. So this is E1 of x plus E2 of x. Right? So the electric field that you feel at that point is due to the electric field from this wave plus the electric field due to that wave. All right? And so, this equals the electric field of 1 at x plus the electric field of 2 of x, quantity squared. And this is what allows you to interfere. Okay, and usually I have everybody do the calculation, but I'm not going to do that today. All right, this is just the idea. Okay, so everybody see that that's how light can interfere with itself and give an interference pattern. Okay, now here's a couple other arguments. Let's talk about probability. Okay. Oh, crap.
So is the energy over the area line, the intensity and the energy?
Yeah, I've wiped that out right there. So this is an E total meter squared second. Obviously.
No, the E is the energy.
Yeah, so this is energy. That's electric field vector.
Okay.
So that's why it's really important when you go home on your notes to really differentiate those things. All right, I'll just say this. I'll just go. Now, here's a point that I'm going to have to make later. All right. I'm now going to take this attenuator and I'm going to crank it up. And so here's the scoop. When the attenuator is open and I put on the light, boom, I get this nice interference pattern, right? Everybody's happy. When I crank up the attenuator, what happens to the intensity?
It should go up. Yeah.
Go up?
No, it goes down.
It goes down. It gets dimmer and dimmer and dimmer. Right?
Oh, yeah, the attenuator is inverse.
Yeah, it attenuates, it goes away. All right? It gets dimmer and dimmer and dimmer. All right? Now, I'm going to crank it up even more. And at some point, you will no longer even see the interference pattern. All right? And I'm going to crank it up a little bit more. And believe it or not, all right, at some point, you will no longer see the interference pattern at all. But what you'll see is little blinks of light here and there. So you'll just get blinks of light. You won't get the whole interference pattern.
That's the one photon at a time experiment.
Okay, and at that point, I've attenuated the light so much that I'm only letting one photon come through at a time. All right, this is the experiment that we do in modern. All right, so now when you get one photon through at a time, instead of getting that nice interference pattern like that, here's what you get. You get a blip. Then you wait for a while later, and guess where the next blip is?
Right in the middle.
Under one of them.
Okay.
Parabolas.
Yeah, I don't know, but maybe right there.
And you go to the other points.
All right, then I wait longer, and there's a blip there. And I wait longer, and there's a blip there again, let's say, and a blip there, and a blip there. Okay, now I let this experiment run for hours and hours and hours and hours, and days and days and days, and I come back. All right, and here's what I find, is the blips here added up to here. The blips here added up to there. The blips there added up to there. The blips there, 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 and so on and so forth.
So it doesn't matter if they're going through one at a time. Even if it's just one photon, it sees both slits.
Okay, so here's the key. Yeah. If I had to say where is the blip